All right, last class we talked about arithmetic sequences. This time we are talking about geometric sequences and 9.3. So your learning target for today is to identify, extend, and graph geometric sequences. So everything we did with arithmetic, we are now doing with geometric. That means you now need to be able to tell if a sequence is arithmetic, geometric, or neither. And then you also need to be able to do all the same things with geometric sequences. Write them, graph them, write them as functions. All right, so first thing, with a geometric sequence, it is different in arithmetic in that it has a common ratio. And so that means that the ratio between each pair of consecutive terms is the same. And when I say ratio, I mean a multiplier. So I am multiplying the same number every single time. The common ratio, if you would like to find the common ratio, you can take one term and divide it by the previous term. So in this example, if I were not able to tell that I was multiplying by 5, what I would do is I would take 5 divided by 1, or 25 divided by 5, or 125 divided by 25, and they would all give me that common ratio of 5. Be careful with this one because dividing is the opposite of multiplying. So if I am dividing, that is still a geometric sequence. However, your common ratio is going to be 1 over whatever number you're dividing, which we will get into. All right, so for example 1, we're just determining if the sequence is arithmetic, geometric, or neither. So I want to see if I am adding the same thing every time, multiplying the same thing every time, or neither of those things. So 120 to 60, if I'm adding, well, I would have to subtract 60. And then 60 to 30, I would have to subtract 30. And then 30 to 15, I would have to subtract 15. So I know it's not arithmetic. Okay, so then I'm going to try geometric. Am I multiplying by the same thing? So 120 times what equals 60? So I'm going to do 60 divided by 120, and I'm going to get 1/2. Okay, 30 divided by 60 is also 1/2. And 15 divided by 30 is also 1/2. So I'm going to see that this is geometric because it has a common ratio of 1/2. All right, part B. So we'll test arithmetic first. So am I adding? So 2 to 6, I would add 4. 6 to 11, I would add 5. 11 to 17, I would be adding 6. So I know it's not arithmetic. So I'm going to try geometric. So 2 to 6, I can see that I would be multiplying by 3. You could also do 6 divided by 2 if you weren't sure. 6 to 11, I don't have something in my brain that tells me what that is, so I would do 11 divided by 6 and find that I am literally multiplying by 11 over 6. So I can already tell not geometric either. So this is neither. I'll use a different color there. Neither. Because it doesn't have a common ratio or a common difference. So it's still a sequence, it's just not arithmetic or geometric. All right, now it's your turn. So try this little chunk of self-assessment problems. Take about 6 minutes to pause the video. All right, so we are checking our answers for the self-assessment. From 7 to 4, I would be subtracting 3, 4 to 1, subtracting 3, 1 and negative 2, subtracting 3. So arithmetic, because the common difference, so we'll just say D equals negative 3. All right, number 2. I can already kind of tell that we're moving a lot more quickly with this one, so I'm going to check geometric first, actually. So 48 divided by 192 is 1 over 4. 12 divided by 48 is 1 over 4. And 3 divided by 12 is 1 over 4. So that means that this is geometric because my common ratio, R, is 1 over 4. All right, number 3. This is kind of weird. It's like growing slowly and then growing quickly, so we'll check both. So arithmetic, I'm adding 5 to 10, I'd be adding 5. 10 to 30, be adding 20, so no. Geometric, 5 to 10, I know that's times 2. But then 10 to 30, that's times 3. So no. So neither. Because we have no common difference or ratio. All right, number 4, which one does not belong? So you're trying to figure out which one does not belong with the other 3. So basically you're trying to figure out which one is, if they're all arithmetic, which one is not arithmetic? Or if they're all geometric, which one is not? So with number 4, you should have found this first one. You're multiplying by 2 each time. So that's geometric. R is 2. This one, you should have also found that you're multiplying by 2 each time, so geometric, and R is 2. This one, I am actually adding 2 each time, so that is arithmetic, and my common difference is 2. And then this last one, we're back to multiplying by 2 each time, so geometric, ratio is 2. So this sequence does not belong because it is arithmetic. We're adding 2 instead of multiplying by 2. All right, number 5. Does the example or the sequence in example 1a eventually reach 0? Explain your reasoning. So 1a, we'll go back up. Would that eventually reach 0? So if I keep dividing by 1/2, 15 divided by 1/2 would be 15 over 2, or about 7.5. 7.5 divided by 1/2, or sorry, not divided by 1/2, times 1/2 would be 15 over 4, and then times 1/2 is 15 over 8. So it's going to keep getting smaller and smaller. But it's never actually going to hit 0 because if I keep multiplying, the only thing I can multiply to get 0 is 0. So no, because my common ratio is not 0. So I will never multiply by anything that will get 0. All right, and then number 6, you would have all had different answers for this one, but writing a geometric sequence with a first term of 8 and a fourth term that is between 90 and 100, you would want to have your starting number be 8, and you would be wanting to multiply by something just perfect so that this fourth number is between 90 and 100. So I think maybe if I multiply by let's try 3. So if I multiply by 3, it's 24 times 3 is 72. Oh, nope, that's not gonna work. Well, I know 2 is too small, so we'll do between 2 and 3. So we'll say 2.5 maybe, 2.5. So 8 times 2.5 is 20, times 2.5 is 50, times 2.5 is 125. That's still too large. Okay, so we will try instead, let's do 2.2. So 8 times 2.2, 17.6. Times 2.2, 38.72. Times 2.2, 85.184. Okay, so that doesn't work either. Oh my goodness. Trial and error, y'all. Okay. We'll do 2.3, and I hope that's not too big. 8 times 2.3 is 18.4. Times 2.3 is 42.32. That's not going to work. Oh, it did work. Yay. Okay. Times 2.3 is 97.336. There we go. Okay. So if we use a common ratio of 2.3, then we can find a sequence that fits that description. Okay. Example 2. Extending and graphing geometric sequences. So extending a geometric sequence is just like arithmetic, except now you're finding your common ratio and multiplying by that. So for example 2a, to find my common ratio, 3 times what is 6? And we know that's 2. So I'm just going to keep following that pattern. So 24 times 2 is 48, times 2 is 96, times 2 is 192. So those are the next 3 terms. All right, B is a little wonky, so you might not immediately be able to see the common ratio. So what we're going to do is we're going to do negative 16 divided by 64 to find our common ratio. And we're going to get that that's negative 1 over 4. All right, so multiplying by negative 1 over 4. Negative 1 times negative 1 over 4 is positive 1 over 4. Then times negative 1 over 4 is negative 1 over 8. Then times negative 1 over 4 is going to be positive 1 over 32. So those are the next 3 terms of that sequence. If you need a refresher on fractions, please either go to tutoring with Ms. Harris or Ms. McKissick, or ask Ms. Whitwer when you have extra time. But please get used to those fractions. All right, I hope that you noticed in example 2b that my signs flipped every single time. So in this math practice where it says look for patterns, the signs will tell you if the signs are all the same, then you're multiplying by a positive common ratio, because you're not changing anything when you multiply by a positive number. However, if your signs change in the sequence, so you have positive, then negative, then positive, then negative, then you're multiplying by a negative common ratio, because that means you are taking the opposite sign every single time. All right, example 3, graphing. We're going to graph the same way we did arithmetic. So we're taking our position in and our term a sub n. So my first term is 32. My second term is 16. My third term is 8. My fourth term is 4. And my fifth term is 2. So I'm going to plot those points. So 1, 32 2, 16, 3, 8, 4, 4, and 5, 2. And then what do you notice? So obviously this is not linear, right? We've got this really fast drop, and then they get a little closer. So hopefully you can connect that this is an exponential function. So it looks like an exponential function. You may even remember from Algebra 1 that that's exponential decay because it's declining. But if not, that's okay. We haven't gotten to exponential functions in class yet. But geometric sequences are exponential functions. They could be exponential growth or decay, though. This one is decay because it looks like we're dividing or multiplying by a number that's less than 1 each time. All right. Take another 6 minutes, work on these self-assessment problems. Pause. All right, let's check the self-assessment problems. Number 7. Explain why the points of a geometric sequence lie on an exponential curve only when the common ratio is positive. So in the case where we don't have a common ratio that's positive, we talked about if you have a negative common ratio, your signs are flip-flopping every single time. So if I have signs flipping, that means I'm going above the x-axis, then below the x-axis, and then back to above, and then back to below. So I'm going to have a graph that looks something like this, which is not an exponential curve, because if I have a negative common ratio, then my signs are changing each term. All right, 8 through 13. Write the next 3 terms of the geometric sequence, then graph the sequence. You may have not gotten to all of these, and that's okay. We will go over all of them just quickly. So number 8, you should have recognized that we are multiplying by 5 each time. So 125 times 5 is 625. And then that times 5 is 3,125. And then that times 5 is 15,625. And notice how I'm not using commas for thousand, so I don't get confused since I'm writing them as a list. Graphing your sequence. So I would have used, we'll say 25s. 75. So we can get at least a few terms in there. And then 1, 2, 3, because we're always going to have just our regular whole numbers there, because that's just the positioning. So my first term is 1, 1. Then we have 2, 5. So we're starting real low. 3, 25. And then we see this exponential growth at 4, 125. And then none of the others would fit on this graph. All right, number 9. You should have taken 256 divided by 1024 and found that you were multiplying by 1/4 each time. So 16 times 1/4 is 4. 4 times 1/4 is 1. 1 times 1/4 is 1/4. All right, so now we're starting really, really high. We'll do 100s. Which is still not even going to fit that first term, but that's okay. All right, so first term is 1024. That's not going to fit. Second term is 256. So we're like here. Third term is 64. So we drop real low. Fourth term is 16. and then we have 4, then we have 1, then we have 1/4. You should notice that it's going to keep getting closer and closer to 0, but never hit it like we said earlier. All right, number 10. You should have taken negative 27 divided by 81 and found that we are multiplying by negative 1/3. So negative 3 times negative 1/3 is positive 1, times negative 1/3 is negative 1/3, times negative 1/3 is positive 1/9. Alrighty. We'll count by 20s. Which is a little too high, but it's fine. Okay, so first term is 81. Second term, oh, silly me, I forgot the signs. We need to have both positive and negatives here. So that actually works out to count by 20s. Okay, so positive 81, negative 27, positive 9, negative 3, positive 1, negative 1/3, and so it looks like we kind of have an exponential function on both sides. If you look at it, it's getting closer and closer to that x-axis. All right, and I lied to you. We're going to skip 11 through 13 just for time. If you guys got 8 through 10, then you should feel pretty comfortable about 11 through 13. All right, if we want to write a geometric sequence as a function, then we still need to know our first term, a sub 1, and our common ratio. And we are going to use this formula right here. A sub n equals a sub 1 times r to the n minus 1 power. All right, so for our first example, I'm going to identify a sub 1 and r. So for example 4, write an equation for the nth term of the geometric sequence 2, 12, 72, 432. So my first term is 2. And my ratio, if I divide 12 by 2, I would get 6. Here, I'll write that for you so you can see where I got that from. 12 divided by 2, which is 6. All right, so using my formula, a sub n equals, replace a sub 1 with 2, replace r with 6, and keep n minus 1. That is my formula. And then find a sub 10, so we're plugging in 10 for n, so 2 times 6 to the 10 minus 1 power. Simplify that exponent, so 10 minus 1 becomes 9. You're going to find 6 to the 9th power first. Which, give me 1 second. I need a calculator, which you will too. So that is, looks like 10,077,696. And then multiply that by 2. So 20,155,392 is my 10th term of this sequence. So you can see it grows extremely fast. All right. Let's take just 4 to 5 minutes on these self-assessment problems, so pause here. All right, we're checking our self-assessment now. Number 14. What information do you need to find the nth term of a geometric sequence? So we just answered that. You need to find, or you need to know your first term and your common ratio, because that's what we plug into our formula. All right, 15 and 16, we are finding our equation and then finding a sub 8, or our 8th term. So to find the equation, we're finding first term and common ratio for number 15. First term is 1. Common ratio is -4. So my equation is a sub n equals 1 times -4 to the n minus 1 power. You could also simplify this and rewrite it without the 1. That is up to you. So to find a sub 8, I'm plugging in 8 for n, so -4 to the 8 minus 1 power is -4 to the 7th power. So if I take -4 and I raise that to the 7th power, I'm going to get -16,384. All right, number 16. First term is 2. Common ratio is 3. So my equation is a sub n equals 2 times 3 to the n minus 1 power. And then I plug in 8 to find the 8th term. So 2 times 3 to the 8 minus 1 power. So 2 times 3 to the 7th power. 2 times, and then 3 to the 7th power. I get that that's 2,187, and then multiply that by 2. And we get to the a sub 8, or my 8th term, is 4,374. All right, just like with arithmetic functions or arithmetic sequences, you can use function notation just by replacing a sub n with f of n. All right, so example 5, modeling real life. We've got this situation here. Clicking the zoom out button on a mapping website doubles the side length of the square map. After how many clicks on the zoom out button is the side length of the map 640 miles? So I want to know at what point does this become 640? So this is my n, and this is my a sub n. So the first thing I want to do is find my equation. So a sub 1 and r are what I need. My first term is 5. My common ratio, it looks like I am multiplying by 2. So r is 2. So a sub n, my equation, or let's do function notation for this one so you see both. F of n equals 5 times 2 to the n minus 1 power. All right, and when it asks after how many clicks on the zoom out button is the side length of the map 640 miles, we are talking about when the f of n is 640. So I'm replacing f of n with 640 and solving for n. We have not talked about this in class yet, so I do not expect you to get this immediately. It is going to take some practice. If for right now all you can do is get to this point, then that is okay with me, as long as you know what to plug in. If you want to take it a few steps, you can divide both sides by 5, because we're solving for n. So 128 equals 2 to the n minus 1. And then if you are aware of how to solve exponential functions, then you could continue this problem, but we are going to stop right here for now. All right, so self-assessment, we are not going to worry about number 22. Actually, we are going to worry about number 22. I want you to set up your equation, but do not solve for n. and then answer number 23. So take 4 minutes, pause. All right, 22. You should have set up your equation to look like this. And then if you wanted, you could have divided by 5 and gotten 1,024, sorry, equals to the n minus 1 power. All right, number 23. The sequence 102, 102, 102, 102 represents the temperature in degrees Fahrenheit of a hot tub over time. Is this sequence arithmetic? Is it geometric? Explain your reasoning. What can you conclude? Arithmetic. Am I adding the same thing every time? Yes. I'm adding 0 every time. Geometric. Am I multiplying by the same thing every time? Yes. I'm multiplying by r every time. So it could be either one. All right, so that is it for geometric sequences. Please make sure you understand the difference between arithmetic and geometric, and you remember those formulas for both of them.